So we have our second talk, which will be given by Aline Tomescu, who is head of cryptography at Aptos Labs. And he'll talk about getting distributed randomness using weighted VRF. Aline?
Where's the clicker? All right. Hi, everyone. My name is Aline. I'm the head of cryptography at Aptos. And today I want to tell you about one cryptographic effort we've made on distributed randomness from a new cryptographic primitive we call a weighted VRF. So this is joint work with Saurav, who just kindly introduced me, Benny, and Daniel. And the TLDR for this talk is the following. We have a proof-of-stake randomness beacon on the Aptos network. So what this means is that there's an on-chain randomness API that smart contracts can call, so precompiles in Ethereum. So for example, a function that returns a random integer between min and max. And this API is instant. You call it, it instantly returns to you the number. And it's cheap. You don't have to pay an external oracle to get your randomness. You just pay the Aptos validators to validate your transactions. And the beacon is unbiasable and unpredictable under the same proof-of-stake assumption that secures the Aptos network. And we do this using a mix of cryptographic primitives such as VRF, PVSS, and non-interactive DKG. So what might you care about this? Well, I think of this from two perspectives. So if you're an academic, you might enjoy this new PVSS for group element secrets that I'm about to show you. It's actually 11 times faster to verify than the state-of-the-art scrape PVSS. You might also enjoy this weighted VRF construction that we're proposing, which has constant share size independent of the weight or stake of a validator. And this is kind of theoretically interesting because it circumvents some lower bounds on weighted secret sharing. And lastly, you might appreciate how these ideas that we have here for the weighted VRF actually extend to other crypto systems like weighted threshold decryption and probably more. So now if you're a practitioner, you probably don't care too much about what I just said, but what you might appreciate is that we'll give you a shorter and slightly faster to verify weighted VRF construction. So this is an alternative to using the naively weighted BLS VRF construction. We also have the fastest non-interactive DKG for group elements, which for you as a practitioner might matter if you care about saving computational cycles and lowering your AWS bills. And as another benefit, this NIDKG, I argue, is simpler to implement and debug than typical interactive DKGs. And this is for a lot of reasons. It's based on publicly verifiable secret sharing. The scheme is aggregatable, so you can post the final transcript on chain. And it lacks this complicated complaints phase, which is a pain to implement and a pain to debug and test. And this DKG is compatible with not just our weighted VRF, but also other crypto systems like the GJM21 threshold VRF and threshold decryption from El Gamal. Another reason why you might care about this is that randomness is very powerful. So if you have randomness, you can build D-apps like games or raffles. You can solve hard problems in consensus like asynchrony. And you even have some nice implications on privacy. So for example, if you have on-chain randomness, you can interactively verify zero-knowledge proofs and reduce the proof size and the verifier time. You can generate keys securely. And you can even have some surprising applications to blockchain accounts that are bootstrapped from Google accounts. So we call this a keyless account. In fact, there will be a talk today about this topic called ZK Login at 4 p.m. I encourage all of you to see it. It's going to be a really cool system. So the outline for the talk is as follows. I'm just going to give you some background on how to get randomness from this VRF threshold paradigm. Then I'm going to talk about weighted DKGs and how they instantiate the VRF. And then I'm going to talk about how to instantiate the DKG using publicly verifiable secret sharing. So this is just the background. Most of you will probably already know this. And then I'm going to go into our actual constructions. So how do we get an unweighted PVSS? How do we weigh it? And then how do we get a weighted VRF? And lastly, I'm going to mention a few things about the deployment of this randomness feature on the Aptos network. Great. So let's begin by talking about randomness. How do you get randomness from VRFs? Well, first of all, what is a VRF? I'm not going to describe it in detail. I'm just going to give you an example. A BLS signature over a message defines a verifiable random function, or a VRF. In practice, you have to hash it, but I'm ignoring that here. So any unique signature scheme that is hashed gives you a VRF. So if you want to get randomness from a VRF, if you have a guy in the sky that'll gladly evaluate for you this VRF under a secret key, it's very easy to get randomness. All you have to do is for each block I in your chain, you evaluate the VRF on either the block number I or the block contents. Here I'm using the block number. So that basically produces this randomness Ri for each block I. The problem, of course, is that who is this guy in the sky, because he will know the secret key, and if he knows the secret key, he can predict the randomness ahead of time, which makes it completely useless. And one answer is, well, let's implement this guy in the sky on the validators. And the way we're going to do that is we're going to use distributed key generation, but because we are in a proof-of-stake cryptocurrency, we're going to need to have a weighted distributed key generation. What does that mean? Well, it means that you have this fancy schmancy cryptographic protocol, which we're not going to discuss too much, but at the end of this protocol, each validator I ends up with a secret key SKI, a secret key share SKI. And the nice property that you have is that for any subset of validators with enough stake, they can reconstruct the shared secret SK by plugging in their secret key shares. So from any 66% of the stake, you can collect shares and get SK, but from less than 66%, you learn nothing. Yeah, so that's a weighted distributed key generation. And is this enough for randomness? Well, actually it's not, right? Because what we actually want is, we don't just want to have a DKG, but we want to be able to reveal a VRF under the shared secret over the block number M, yeah? So we need a weighted verifiable random function protocol on top of this DKG after it's finished. And how does the weighted verifiable random function work? Well, it's a protocol that will allow each validator to compute locally a VRF share under their secret key share over the block number M. And then the nice property that you'll have is that, again, once you have a subset with enough stake that combines these VRF shares, you can reconstruct the final aggregated VRF that you see here, yeah? Good, so now that we know how to get randomness from weighted VRFs and from weighted DKG, let's talk about DKGs. And for now, I'm going to stick to the unweighted setting. I'll describe later how to actually weight the DKG. So I'm going to describe to you how to get a weighted DKG, so how to get an unweighted DKG from an unweighted PVSS. So here we're talking about a T out of N unweighted publicly verifiable secret sharing of some secret S. So what is this? It's just a scheme that gives everyone shares of S such that any subset of size greater than T can reconstruct S from their shares. So for this to work, you'll need a public key infrastructure. So each player I will have a decryption key, DKI, and an associated encryption key, EKI, which typically looks like that. And there is a dealing algorithm which takes the shared secret S and the threshold T that you want to share it on and the encryption key of the validators and outputs a PVSS transcript. And at a high level, I want you to think of this as just encryptions of each validator's secret key shares under that validator's encryption key. So we say that this transcript deals the secret S in a T out of N fashion in the sense that it splits it amongst the validators. And then there's a verification algorithm which actually checks that this transcript does so correctly. And lastly, in some PVSS schemes, you have this really nice property called aggregation. So you can take two transcripts for two different secrets, S1 and S2, aggregate them into something succinct, and that succinct aggregation will actually deal the sum of the secrets. So this is a nice homomorphic property that you get, and this will be very important when doing DKGs. As I'm about to show you, if you want to do a DKG from a PVSS scheme, it's actually very simple. All that you're going to do is you're going to deal secrets in parallel. So each validator I will pick a random secret ZI, will deal it via PVSS to the other validators with threshold T, and that defines a transcript TRXI for validators I secret. And then there will be some subset of validators, large enough subset, that have done this correctly by the threshold assumption. And then we can identify the subset by calling PVSS verify on each transcript. And actually, this will be the bulk of the cost of doing a DKG, will be doing this PVSS verification. And then once we've identified the subset, we can aggregate the transcripts into a final one. Yeah, in this final transcript, we'll actually deal this shared secret SK, which is the sum of the ZIs of the eligible correct validators. Yeah? So as you can see, it's a very simple protocol. You just can think of it as dealing PVSS in parallel, figuring out who did that correctly, and then defining that as the shared secret. And again, the property that you get is that no subset of less than or equal to T can reconstruct the secret key, but only subsets of greater than T can do so. So that's how you get a DKG from a PVSS. Now, how do you weigh it? I'm going to mention that in this part of the talk. So this part of the talk is about our unweighted PVSS construction. So before we can go into it, you have to have a few preliminaries. This is the cryptography session, right, Saurabh? Yeah. Okay, so we're going to talk about type 3 pairings, which some of you should be familiar with. We're going to talk about having a bunch of generators in some of these groups. And we are now ready to introduce the scheme. So how do we implement dealing? So let's say I have a secret A0 that I want to deal in a T out of N fashion. Here's what we're going to do. We're going to define a degree T polynomial by picking some random coefficients. So this polynomial will have coefficients A0 through AT, and P of 0 will evaluate to the secret. So I'm sure many of you have seen this. This is called Shamir secret sharing. If you haven't, enjoy. It's a really nice, beautiful primitive. And then once you've done this, once you have this polynomial, we can evaluate it on points 1 through n and commit to these evaluations. So these will be actually commitment to the secret key shares. And once you've done that, you simply encrypt for each validator their share using an El-Gamal-like encryption. So this is a batched version of El-Gamal that uses some shared randomness R and encrypts for each validator I its PI. And this defines the transcript. The transcript will be the El-Gamal ciphertext and these shared commitments. And the secret key share of each player I will just be a group element, h raised to p of I. That is the secret key share of a player. And the final dealt secret will be h to the p of 0, so h to the a0. Yeah? And the nice property that you'll get is that given enough SKIs, so given more than t, you can aggregate the SK via what some of you know already as Lagrange interpolation, which I'm going to mention later. Okay, so how does this perform in practice? So if we do this in a T out of N setting where T is 548 and N is 821, those were the initial numbers we used in the Aptos deployment, then you can actually do a dealing in 208 milliseconds. And this is actually a little bit slower than the state-of-the-art scrape protocol because we have some extra elements here, this V vector that scrape doesn't. But as I'll argue later, that doesn't matter because we win in other parts. And the transcripts are pretty small too, 154 kilobytes, and they're aggregatable because as some of you may be able to tell, these guys here will have really nice homomorphic properties. Okay, so the reason actually that performance worsening doesn't matter is because our verification will be much faster. So let me show you how verification works. I have my transcript here that I just presented to you. We're going to do something called a low degree test, and for this we're going to use the scrape low degree test. This simply checks that the polynomial committed in here, which is committed by committing to the evaluations, is a degree T polynomial. That's what this does. It does it via multi-exp, so it's very efficient. And then we're going to check that these shared commitments have the same thing in the exponent using a pairing. So this just checks that VI and VI hat commit to PI in the exponent. And then we're going to do the same for this El-Gamal randomness here, which is going to check that it has R in the exponent. And lastly, using a pairing, we're going to check that the El-Gamal ciphertext encrypt the same P of I's that are in these commitments. And I'm not going to explain why this works. I do have a slide in the appendix if you want to see intuition for why this works. And there will be a link to the slides later on. And one way to look at our PVSS is it kind of combines the best of both worlds, the scrape PVSS and Grotz's recent PVSS for field element, which is a really nice construction. But in practice, if you want to implement this, you're not going to do it like this. You're going to be a little bit more sophisticated. You're going to take a random linear combination of these pairing equations and combine them and take advantage of right-hand sides being the same and left-hand sides being the same. And you get something much, much faster. So you get an equation that we can verify in 21 milliseconds, which is 11 times faster than the state-of-the-art scrape protocol. And this matters a lot because if you remember, I mentioned earlier that in a DKG, we have to do a lot of PVSS verifications. So each player deals once, but each player could verify up to T transcripts. So verification time is way more important. Okay, so that was unweighted PVSS, and we know how to go from unweighted PVSS to unweighted DKG. If I have a weighted PVSS, the same transformation will apply, more or less. How do I get a weighted PVSS? The answer is I'm just going to use the most naive approach you can imagine, virtualization. What does this mean? So if I want to get a weight T PVSS, target weight T, where the total weight is N, and each player I has weight WI, let's, for example, assume that these are the weights of the players. So player 1 has 3, player 2 has 2 weight, 1, and so on. Here's how I'm going to do it. So I'm going to do a normal unweighted PVSS with n is equal to 8, and I'm going to get my shares here that I showed you earlier. And now I'm just going to carefully assign each share to a player. So the first 3 shares go to player 1 because player 1 has weight 3. The next 2 shares go to player 2 because player 2 has weight 2, and so on. Yeah, so in general now, each player I, their secret key share in the weighted setting will just be a bunch of WI subshares, which are assigned in this straightforward manner via virtualization. And we still have the nice property that for any subset S of weight greater than T, we can reconstruct the secret key dealt by this transcript here from these weighted secret key shares. And the way that reconstruction is going to look like is it's going to use Lagrange interpolation. So I'm going to have some Lagrange coefficients that are computed from the set of players. And then I can do one large multi-exp and interpolate my secret key. It's going to look like this. And that takes care of weighting. OK, so now we have a weighted DKG. How can we get a weighted VRF? Here's our construction for that. So what we actually are going to do is we're going to come up with a protocol that allows the validators to aggregate this final VRF, which looks like this. So this is the secret key from the DKG. And you might notice this is kind of a BLS-like VRF. It's just that instead of exponentiating, we're pairing with a secret key. And the first time this construction was proposed, I think, was in the GJM21 paper, which is cited in this talk. And obviously, we don't have the secret key, so we're going to have to sort of aggregate this final VRF from the secret key shares of each player I. And what we're going to do is we're going to play with this equation. So I have the same right-hand side here, so I can actually move the product out of the pairing, and I'll get this equation here. And I can also pull out the exponent outside of the pairing once I move the product out. And here I want you to focus on this particular element. I'm going to call this a partial VRF evaluation. Right? So if I have a bunch of these partial VRF evaluations for an eligible set S of validators, then I can compute the Lagrange coefficients and I can get my final VRF and I'm done. The question is, how do I get these? Like one naive answer is each validator computes it, but that would actually not have constant share size. And another question would be, how do you verify it if you were to do that? So here's how we actually handle that problem. So what we do is, after the DKG finishes and the validators have their shares, we do a post-DKG local key generation phase. So each validator I will pick some randomness Ri, and will commit to this randomness. And then, for each share of validator I, they will randomize their secret key with this Ri, and compute what we call an augmented public key. And then the validator I will broadcast their augmented pub key together with this Ri commitment to all other validators. So now everyone has everybody else's APKIs. And the way we're going to sign and get a constant size VRF is we're simply going to do a BLS-like signature on the block number using 1/Ri as the secret key. And this is constant size. It doesn't matter how much weight you have. You're always just sending one group element. And you'll notice that this is actually verifiable against the commitment to Ri using a BLS-like verification. And now here's how aggregation works. So what we observe is that for any j from 0 to wi, we can pair APKIJ with the sigma I. So what do we get? We're going to swap out these guys. Sigma I is this, APKIJ is this. We're going to get something that looks like this. And because of the bilinearity of the pairing, we can actually cancel the Ri's, and we'll get exactly this element that I told you is sufficient to aggregate the VRF. And we're done. And this is how we get constant share size for the VRF. OK, so how does this perform in practice? So I'm evaluating this on the initial Aptos deployment, which had 112 validators. Threshold weight 548, and total weight 821. And the weight are distributed kind of in a power law-like distribution. So there's some validators who have a lot of stake, and some validators who have very little stake. And so we're going to compare this with what you might normally try and do. You might normally try to weigh BLS in a naive fashion by doing virtualization. And we're going to look at the average case, because all of the complexities I'm described are deeply dependent on the subset of validators that you aggregate from, or that do the share signing or the share verification, because those validators will have different weights. And those weights affect the complexities, for example, in the weighted BLS scheme. So in the average case, we just kind of consider all possible sets. We sample. So let's look at the time to produce that VRF share that I just showed you. So in the BLS, this time will depend on the weight, so it's a little bit slower than us. It's 2x slower on average. Now, the time to verify suffers from the same thing. In BLS, the share size will be linear in the weight. In our case, it's constant, so we tend to be faster on average. Same thing for the share size. It depends on the weight. In our case, it's constant, so we're going to be smaller. On the other hand, in terms of aggregation, BLS does much faster, because BLS needs to do one G1 multi-X with the Lagrange coefficients. We have to do a multi-pairing, if you recall from the previous slides. So we're 10x slower in terms of aggregation, but actually, in terms of end-to-end time, it doesn't really matter, because most of the time is spent in share verification. And we have very high winnings there, so we come up better on the end-to-end time. So all to all, we save in communications, and we still slightly better in terms of computation. All right, so this kind of brings us towards the end of the talk. Just want to mention the deployment on Aptos. I hope I still have time, Saurav. So we deployed this on the Aptos mainnet on June 2024. And as far as we can tell, this is the first time you see a proof-of-stake randomness beacon that is unbiasable, unpredictable, and operates as fast as the network. So this is to contrast it with VDF-based approaches, which would not be as fast as the network. By the way, that's a great open problem to work on. So since we deployed this, we've seen 500,000 transactions that call this randomness API. And our DKG lasts about 20 seconds. So every time the validator set changes, we start a DKG. The old validator is dealing a secret to the new validators, and that lasts 20 seconds. Our randomness latency, which is the latency measured from the time a block is committed to the time the randomness for that block is available, was initially 160 milliseconds, but we were able to bring this down to 25 milliseconds using some optimizations by Saurav, Daniel, and friends. Fast paths, BFT, quorum intersection, you know, fun stuff. Great, so to conclude, I'll leave you with a question here. What can switching to group element secret keys do for you in your system? So for us, it's helped us a lot with performance and simplifying the code base. So I showed you a PVSS for group element secret keys, which is the fastest aggregatable PVSS to date. And it yields the fastest non-interactive DKG, which I argue is probably what you want to implement in a system, because it's very simple to do so, and it's very easy to debug and test. And then I showed you the surprising order 1 weighted VRF construction that has practical utility. I showed you how we deploy this on the randomness, how we deploy this randomness feature on Aptos. And everything is open source. You can check out our code there, the DKG, the VRF, some baseline schemes that we compare to. And here's a QR code for the slides. And I want to thank a bunch of people that helped us with this work. So Sasha for giving us the idea to work on randomness, Georgina and Zakun for engineering, Dan for helping us with security analysis and general advice, and the broader Aptos Labs team for production readiness of this feature and deployment, which, believe me, is in a way harder than everything I just showed you. And there's many things that I did not get to discuss. I'll leave this in the slides. You can take a look at them. And I'll leave you here with a quote that I found recently and it's been in the top of my mind. And with that, I'm ready for questions. Thank you.
Thank you, Aline, for the amazing talk. We have lots of time for questions.
Hi, Aline. Thanks for the talk. Super informative and exciting. I wonder how would it look if you're using an elliptic curve-based system or something more MPC-based? How would the performance or like caveats be?
What do you have in mind? So this is elliptic curve-based, and it technically falls into the paradigm of MPC. Like a DKG is an MPC, and a threshold VRF or a weighted VRF is an MPC. So do you have a particular scheme in mind, or?
So just wondering why you chose this particular one.
Oh, why we chose this over weighted BLS, for example, or?
Like over other primitives?
Yeah, I guess broadly speaking, the reason we chose this non-interactive DKG is because interactive DKGs have two problems. First, you cannot start the DKG on the old validators and deal a secret to the new validators because the new validators aren't even online yet, right? Like you have to know who they are. So they have to be online and interact. With a non-interactive DKG, you can non-interactively deal to the new validators once you know their public keys. So that's one reason. So this allows you to enable randomness the moment the epoch changes in the consensus protocol, because otherwise you would have to sort of defer randomness transactions until the DKG finishes. So that's one reason for the non-interactive DKG. The reason to do group elements over field elements is, I would say, efficiency. It's going to be way more efficient to do group elements in terms of the DKG. And then in terms of the VRF, the reason to do group elements is because you've done a DKG for group elements. But one other benefit that we got kind of for free is that we can reduce communication while maintaining and slightly doing better in terms of computation. So those were kind of the main reasons. I hope that answers the question.
Yeah, super helpful. Thank you.
Oh, hey, Madi.
So one clarification that I would like to know. You mentioned that if the validator is churning, you need to run the DKG again.
Yes.
It shouldn't be if the stake are going to be changed, you need to rerun the DKG.
Well, even if the stakes change, you need to rerun it, right? Because they might change by so much that the reconstruction invariant will no longer work. If they change slightly, maybe you could keep going, but yeah.
Exactly.
I guess by validator set changes, I'm accounting for the stakes changing.
The stakes. Okay,
yes.
So you are moving everything to the target group that we know they are slower and also larger in terms of efficiency and also the size of the elements. Mm-hmm. How do you, consider this? And also, is there any hope to bring them back to the source groups?
Yeah, so, well, the good news is actually that even though the final aggregated VRF is an element in GT, other than that, there's no GT elements that ever arise in our protocol. So everything happens in G1 or in G2. Yes, we aggregate this thing in GT via the multi-pairing that I showed you on the slide, but once we have that thing in GT, we just hash it to get a VRF, so we get a 256-bit VRF, and we're done. So that's literally the only place where you'll ever see a GT element is the product of the aggregation, and by then you're done. So it doesn't matter.
Thank you.
Yeah.
Hi.
Hi.
Thank you for the talk. Robert McLaughlin from UC Santa Barbara. I'm interested in, so you mentioned that it's secure under an assumption of 66% honesty of the network, but if there's collusion, obviously you're going to have issues.
Yeah.
And I'm wondering about, because you flashed on that last slide, collusion mitigation. What possibly could you do? 66%, I mean, it seems good, but also in Ethereum, right, when we saw MEV-Boost come out, it very quickly was adopted by like 90% of the network plus.
Yeah.
So how do you believe it could be resistant against?
Yeah, I'm really glad you asked that question, because that is the million-dollar question. So I think for the research community as a whole, we should spend some time thinking about this. The only answer I have is you make these systems collusion resistant by throwing a trusted execution environment to protect the secret key. Because otherwise, you're exactly right, you can collude an MPC. If you have a fair MPC, you can reveal the shared secret, right? And it's really easy to get a fair MPC because you can do it in a trusted execution environment, right? So you're done. So the only sort of defense in depth technique that you have, as far as I can tell, is to, once again, use a T to protect the secret key. Yeah, if you see anything better, do let me know and we can chat after. Yeah.
Thank you.
Yeah.
Hi, thanks for the talk. I was wondering if you have any thoughts or if you think there's any hope in finding something maybe more efficient than the virtualization technique that you described. So something that doesn't assign a number of shares that's linear in the weight of.
Yeah, I'm sure there are people here who can better answer that question than me, secret sharing people, but as far as I know, there is this Amos Baimel paper called Characterizing Ideal Weighted Secret Sharing Schemes, and that paper shows some lower bound. That weighted secret sharing schemes, the share size cannot be constant. So that's just for secret sharing. That doesn't imply anything for VRFs, which is why we could get this result. How that can be circumvented, I think, is an open question, if it can be circumvented. Do you have something particular in mind?
Certainly not a constant number of shares, but something that's logarithmic or using some other ideas, I don't know.
Yeah, right. And there have been some papers, I think Sanjam Garg had some papers on weighted cryptography, and there may be, I don't know asymptotically if they do better than linear in the weight.
Maybe I will ask for the reference afterwards.
But it's a great question. It's a great question.
Right.
I think with proof-of-stake blockchains, it's worth
investigating.
investigating.
Exactly.
Yeah.
Thank you.
Okay, let's thank Aline again.